Okay, our next panel is the REV H panel. I want to introduce Kevin Clements. He is our IT chair for the South Wireless Summit, so all the stuff you see flashing around here on screens, he's responsible for. Kevin also serves on the board of the Ohio Wireless Association, and he's a de facto member of the Kentucky Wireless Association, so that's why we let somebody from Cleveland be on the South Wireless Association board. So, thank you, Kevin, for all the hard work you do for us in the background, and you can go ahead and take away with your panel.
I'll start that off with Go Browns for all those that care.
Football team.
Yeah, they are now.
They are now, yeah.
So we wanted to briefly go over REV H and some of the topics that REV H hits on. It's an applicable code now. It was effective on January of 2018. And now more and more states are starting to adopt the code, with 2 states that have waterfalled statewide, Puerto Rico, and more local jurisdictions and cities starting to adopt it. In addition, many owners are proactively adopting the code. 1, because it's just more accurate and provides a better structural analysis of the tower, and 2, because there are some added benefits within the code. With that, this panel aims to dive into 14 high-level topics that adjust your towers, and we'll go into if those benefit or maybe are neutral on the site. I wanted to introduce the panel. To my immediate right is Brian Lanier. Brian has over 17 years of telecommunications experience. He's currently the Director of Broadcast Engineering at American Tower, and he sits on he's the Secretary of the TR-14 Committee, which currently writes and submits the code. Next to him, Tyler Stevens. He's currently the Structural Engineering Manager at Crown Castle. He's an active member of the TR-14 Committee, and he works closely with 20-plus engineering firms, pooling their information and helping host forums to decide on future engineering. Next is Michael Oglesby. He's also a member of the TR-14 Committee and sits on a subcommittee dedicated to mount analysis. In addition, he's a certified climber and tower rescue instructor, and Michael is currently a structural engineering manager at Kimley-Horn. With that being said, we want this panel to be very interactive. Am I changing? Could you hit the next? Thank you. So our aim is that this panel be very interactive. We have several topics, and to be honest, we're not going to be able to get through them all. That being said, we're engineers, so we're going to go in alphabetical order unless anyone tells us otherwise. And with that being said, I'm also going to disappear into the back of the room to help kind of run the presentation because it has a lot of embedded links in it, and I don't have a workable laptop up here. So as you come up with questions or want to hear on a specific topic, please let us know. Just so you guys know, the green topics are things that potentially help structural capacity, allow for further co-locations. The yellow are more neutral subjects or new additions to the code, and red are things that potentially can decrease capacity of the structure throughout its life. We'll move on, and I'll start it off with allowable capacities and grandfathering. Again, alphabetical order, and it's my favorite one. And with that, I'll turn it over to Tyler to discuss what the allowable capacities and grandfathering means in the industry.
Okay, so as many of you are aware, for many years throughout the industry, in terms of structural analysis, typically owners and engineers have considered a structure acceptable up to 105% of what the code dictated demand capacity ratio of that structure was. REV H is the first instance where that's been incorporated into the code itself. Although for years it has been industry-wide standard of care and practice. The benefit of adding this section into the REV H standard is to bring clarity to any jurisdictions, as well as to set a baseline for engineers in evaluating when really is the appropriate time to look at retrofitting an existing tower when you are just beyond what the requirements would be for the design of a new tower. Similarly, within REV H, there's been an expansion of the existing structures addition section, which defines what a significant increase in loading is and dictates when you need to bring a tower up to the newest standard that is the minimum requirement of the jurisdiction. This is more in line with what was in the IBC for years and provides consistency and clarity of application.
Thank you, Tyler.
Also, further things to add to that, support Tyler's comments. A lot of what I do is broadcast engineering in American Tower. A lot of the comparison to the old ones is you have a lot of towers that were built, especially in the broadcast industry, that were built 30, 40, 50 years ago. Were never built to even Rev F standards, much less Rev G or Rev H. So the idea is that you don't make some of these towers basically obsolete or unusable structures anymore. So that was the intent of this portion of the code, among other things.
Perfect. And as you guys have questions, do feel free to raise your hand. I can run around with the microphone and chase you down. With that being said, let's move on to some anchor rods and grout consideration that have been recently addressed in the code. Tyler, if you wouldn't mind again, kind of running us through what the impact of section 14.99 is.
Sure. So while Rev H does offer a lot of capacity additions for carriers and tower owners, there are a few instances where we are faced with more restrictive requirements. Probably the most impactful is the additional requirements around anchorage and the usage of grout under tower legs at the base. So with Rev H, grout is no longer considered applicable as a vertical load carrying member. The impact to this is then it must be carried through the anchor rods themselves in compression. Now this is a deviation from the way a lot of these structures were designed and constructed, and you can see some negative impacts. That impact increases as the tower leveling nuts were raised and you have a larger, essentially mini column being formed by that anchor rod, and it can have to take that vertical load, but it could also induce bending that rod. This is one of the introductions into Rev H that really was brought over from the general steel and building industry. So I think there is definitely a lot of focus on the TR14 committee on how to continually look and improve this moving forward. But you definitely see some negative impacts regarding the elimination of grout as that vertical load carrying member and putting that load through the anchor rods. One of the strong benefits of introducing this requirement is that grout, which has historically been a large maintenance issue on structures, can now be eliminated because it's not posing that structural benefit, but that maintenance challenge and cost associated with it.
So part of the other motivation for including this in the code is evidence that this could potentially be a problem really comes from the wind industry. So in the wind industry, wind turbines that are set up, anchor bolts with fairly long extensions out of the concrete that aren't grouted properly or have poor grouting techniques have exhibited problems. We've seen examples of where these things have snapped prematurely or broken off completely. So that's not the only entire reason, as Tyler mentioned. It's really to provide alignment with the steel industry standards. But there also has been some examples in other industries where this potentially could be a problem, which may reveal itself, or could potentially reveal itself in the telecom industry as well.
Excellent. Let's talk about angle strengths and some of the inclusions or congruencies TIA adopted to better align with the ASCE 10.
So, in this case, this is probably one of the places where you see a significant increase in structure capacity. So this is something that came from ASCE 710. One of our members on our steering committee is a part of this as well. That's Dave Brinker that works with Rona Industries. Effectively what this does is the American Institute of Steel Construction, AISC, provides certain design criteria, certain equations that engineers use to assess how strong a certain steel member is. And that assumption is true for any type of shape, whether it's an angle, if it's a big I-beam, if it's a pipe, anything. The reality is all those different shapes have different ways in which they will buckle, or when you compress them, how they'll react to it. In ASCE 710-15, is the latest publication was in 2015, which is YS-15. there was a significant amount of testing that's been done over the years that's sort of proven that those equations are actually quite reliable and are significantly stronger than what we've been using in Rev G. So we put that into we basically built this in the Rev H. The net result of this is we see the angle members, which effectively you see a tower is usually your diagonal members or your horizontal members, can increase as much as 11% to almost 30%. So you're looking at a pretty big increase. What ended up happens is that in the past where the member may have controlled a compression is now controlled by your bolt connections, or the way it's connected to the tower becomes more critical than how long the member is, how big the member is.
Yeah, this is a very good instance where specific testing can lead to increased capacity. Yeah. ASC 10 deals with structures very similar to those ones we deal with in 222, and therefore by being more specific and doing that unique testing, we were able to drill down to more exact results, whereas the primary equations within AISC are dealing with use cases of angles in any structure. And with that, you have to consider a much broader use case.
Other codes in Europe, for example, European Eurocode standard or Eurocode, this is pretty common practice. So this is actually a case where in the United States, we're starting to catch up with some of the more international codes, which is taking a more aggressive stance on how to assess the strength of new structures and existing structures.
Excellent. Let's talk about, as we know in the industry, a lot of the failures associated with towers are due to corrosion or some sort of fatigue. Let's talk about the new corrosion control aspects that have been added to the code and what the impacts are, or what that kind of controls.
So where this comes into play, this has been, I don't know how widespread it's been known, but I think it's fairly well understood that when you have a guide tower, those guide towers have anchors that go into the ground and usually have steel rods that basically interact directly with soil. And there's been concerns in the past about how well those steel rods survive any type of corrosion within the soil. And it's really a challenging thing as opposed to what's above grade, is you can't see it. And there have been examples of towers that have collapsed because of steel rod corrosion. So this is something that we put in Rev H as well. Not really something that's mandatory from the standpoint of you have to check this box as much as it's expected that this is the owners of the site should have some type of site-specific assessment and some kind of management program. So effectively, you're putting the onus on the owners to keep track of this, to make sure you have a safe structure and a safe site. The idea of a site-specific assessment doesn't mean you go and dig every anchor up. It doesn't mean you're doing some kind of specific testing on every site, but you do have some kind of program in place to assess risk, be it on the type of anchor, the type of soil, the location, the environment, how low the tower is, how much people climb it, how large the steel is, and then if you want to take it further and do some digging and do some larger assessments of where your really risk is, where you expect to see corrosion, where you expect something to see much more reliable. This was something that was expected to be put into as part of your ownership, part of ownership's maintenance program. So, but this impact really is it does create a greater awareness that this is something to be concerned about. If you think about towers, it really takes a pretty good bit to make a tower collapse. It's not, doesn't happen all that often. They're quite robust. But something could cause a tower collapse. There's very few things that could probably make it happen instantaneously without someone noticing it right away, and anchor conditions are one of those things. So inevitably what you've done by this, or what we expect will be as a result of this, is you should see a greater level of reliability and confidence in the anchors of guide masts that should be able to sustain larger winds and as well as people working on them.
Thank you, Brian. With one of the more attention-drawing topics in the industry is drones. And TIA also took note of that and included some language in Annex J about the use of drones and their limitations. Mike, can you go into kind of what that includes and how drones can be practically used per the TIA?
Yeah, sure. You know, drones are a hot topic in the industry right now. There's a significant amount of R&D going into the technology surrounding drones and how they can be effectively implemented in the industry. Rev H has essentially adopted some language that has opened the door for the use of drones in the tower industry. What we're seeing right now is the primary technology that's being implemented with drones is LiDAR and a system of photogrammetry. And what that basically involves is flying a drone around a tower and taking a series of both measurements and photographs, and then going back and doing some post-processing. Some ways that that can be actually applied in the industry right now today with the technology we have is through doing simple appurtenance mappings, going up, taking photos of what's actually installed on the tower. As you may know, the equipment is configured and reconfigured quite often, and sometimes this data or the actual installed conditions may get lost. And so flying a drone up is a really effective way of going up and recording that information and avoiding a climbing activity there on the tower. Where we're seeing limited use of drones right now due to a limitation in technology is for actual structural mappings. And in fact, we put in some language in REV H that made the requirements of the measurements quite stringent. And that was because we wanted to make sure that the technology is developed appropriately before people start using drones to map the structure of a tower, which essentially involves going up, taking measurements such as leg thicknesses, member dimensions, things of that nature, where when you're looking at the thickness of a tower leg, for example, a small deviation in measurement can make a significant difference in the capacity that we calculate. So like I said earlier, there's some ongoing R&D trying to develop that technology, but we are seeing more and more availability for the use of drones in the industry. And I think Jay even touched on it earlier. There is a limitation of available labor in terms of tower climbers in the industry right now. And so any chance that, anytime that you can use this technology to maybe supplement the need for a tower climb is a good thing.
I'll say probably the biggest place where I think I've seen it being really impactful is just doing on-site inventory gathering. So assessing how many antennas you have, how many radios you have, where your lines are at, and what specific rad centers are. So show of hands, how many people have had an argument over what the rad center is on a tower? Well, antennas are already existing. They're already in place. Everyone, right? So it's a matter, is it measured from the top of the foundation? Is it from the center of the tower? Is it measured from the compound entrance? Any number of things. That's probably the biggest thing where we've seen drones can get down from measurements of arguments of are we off by 3 to 4 feet to we're off by 3 to 4 inches. So as Michael said, the problem is you can get drones, maybe can get you down to a quarter inch of accuracy. That's fantastic. But we frequently upgrade members from a 3/16 inch to a 3/8 inch or a quarter inch. So that's the difference between a passing or failing tower. So that level of accuracy becomes that important and that critical.
Thanks, Brian. Let's talk about ground elevation factor and kind of the new impact of that consideration in code, and maybe highlight maybe a few cities that are greatly impacted, such as Denver.
Sure. So it's been widely known, not just within engineering, but just the general population. As you go up in elevation, the air gets thinner. And it's been no surprise that thinner air causes, a lighter wind pressure at the same wind speed. And within ASC 7 and the wind engineering community, this has been known for quite some time. However, it's never been practically implemented unless there's been a site-specific study done on any individual project. Well, REV H and the 2018 IBC, this has become a codified part of our standard, and sites that are at higher elevation, which traditionally is a very beneficial place to place a tower, you do see a decrease in the required wind pressures that need to be engineered against. So down in South Florida, unfortunately, there's not going to be really any benefit for this implementation. However, in locations such as Denver, you can see upwards of 15 to 20% capacity improvement on your structure. Sure. So, I would say that a topographic factor is certainly still going to be the more impactful requirement. That can be upwards of 100% increase or greater in the required strength of a structure. So the 20% benefit in those cases aren't enough to balance it out. Where you will see benefit is higher elevation does not need to be on an isolated hilltop, whereas with the application of topographic factors, you do need to be on an isolated elevation. As well, topographic factors have been in the standard for quite some time now, so there are a lot of active structures which have already had those factors applied to them, and now you're just seeing the benefit from the reduction, even though it is still a higher requirement.
And
About down to an eighth quarter of an inch.
Sure.
How come you can get that accuracy with 1/16 of an inch?
Now, I've heard that before.
Yeah, so I think one of the biggest things with drones is it's a tool. And it's a tool that can be a simple drone you pick up off Amazon to a very sophisticated hardware system. So I think what was really the aim is just to make sure that whatever your tool you're using is appropriately qualified for the use case.
Yeah, I think that's probably the biggest thing is, do you see it consistently? Like, there are certainly some drone operators who claim to get down to 16th and can do it, and show results where they can get that done consistently. We've also seen examples where it hasn't really, it's off by as much as 3/8 of an inch, which isn't a huge deal, but it's, when you're talking about structural mappings, it is. So it's a matter of ensuring you get that consistent level of reliability. And I don't know if industry-wide we're there. Certainly, I think there are probably certain organizations that are.
let's move on to talking about reliability factor, which is one of the more interesting things added to the code. And tell us about what needs to, or what the prerequisite is to reap the benefit of that reliability factor.
So reliability factor, this is something that was put in Annex S. This was probably one of the more controversial things that was, I guess as a result, more controversial topic that was in Rev H that as a result Annex S and this modification factor was put in place. Where it started really goes back to sort of using old standards. We talked about grandfathering a few minutes ago and using older standards and comparing loadings to then versus now and what that means. Well, that's using an older standard may not always exactly be the most appropriate thing, although certainly a structure may have demonstrated a high reliability in the field. So as a result of that, there was a lot of discussion on whether that should be taken away as an option. You should only be allowed to meet the newest standard, or can you go back to old standards? And there was great debate about this. Originally, there was an idea about something about the length of the installation was going to be something that was going to be used to assess how much loading should be put on the tower, how much wind, how much ice, how much big your earthquakes would be. But that was shot down because there was the concern that that could be utilized inconsistently, I guess maybe is a polite way to say it, but someone could use it to their advantage and kind of daisy chain your way to putting more and more antennas on a tower while making it significantly less safe without ever any real intention of ever removing any equipment or taking it down. So we decided to come up with this instead. So it's what it applies to is a risk category 2 structures, and we're going to talk about what a risk category means in a few minutes, but it effectively reduces the wind loads and the ice loads on a tower. Basically makes them less. So your tower doesn't have to resist as high loads as it would have otherwise. However, there's kind of a couple of caveats to that. This is not applicable to a brand new tower. If you build a new tower, you can't utilize this at all. You have to design to the higher wind and the higher ice. It also requests that if you're going to utilize this, you have to do consistent inspection and maintenance on your towers. So you can't just say, I'm going to use it and we'll climb the tower in 10 years. You need to be actively in line with recommendations for inspection and maintenance per what TA recommends. So the idea of this is that you're going to make sure your tower's in good shape, that it's not exhibiting signs of damage or it's developing a weak point, that you're going to make sure it's in good condition and it should be able to stand up to a pretty rigorous load. So how you apply it is you apply a 0.95 factor to your wind load, so you get 5% off, and you apply a 0.85 factor to your ice thickness. So as a net result of that, you get about 5% of your capacity back on your tower for a monopole or self-supporting tower. So it's It's not a huge deal, but it adds up. I mean, if you're swapping out smaller antennas for larger ones, that might be the difference between having to upgrade a tower structurally versus not. For guide towers, where you really see the biggest difference in that you can see your usage in your tower go down from 5 to 20%. Mostly because most guide structures, ice loading controls a large portion of the design of the tower. And a lot of towers that were built to Rev F standards, which were built just to a standard half-inch ice. And now the ice thicknesses vary anywhere between 3/4 of an inch to almost 2 inches. So that's a big difference in weight. So using this factor here makes for a much more design that makes a lot more sense, and you have a better assessment of what your reliability of your structure is. So, but again, the key to this is you have to have consistent and rigorous inspection planning. While driving out to a site, looking up at it and saying, well, that looks pretty good, let's go back to the house, is not good enough. You also have to demonstrate that as your inspections have found deficiencies in the towers, that you've made efforts to remediate them, to maintain at least the structural liability. So you're kind of getting anywhere between 5 to 20% back on your tower, but you have to invest in the maintenance of your structure to ensure that its lifespan continues.
Has there been any discussion about codifying how often those inspections are taking place, or what maintenance window timeframe there is for any repairs to occur?
So the inspection cycle is 3 to 5 years per Rev H. So 3 years for a guide structure, 5 years for a self-supporting structure. There have been discussions about potentially extending that, depending on what your inspection cycle records indicate. Like let's say you've inspected a tower for the last 10 years and you've inspected it 3 times, and you found largely you're not finding any real problems with it. Because generally speaking, if there's a problem with the design, it'll reveal itself pretty quickly. It's not gonna be 25 years before you finally realize that a bolted connection was designed properly or wasn't tightened properly. So that's been something that's been discussed. We haven't made an effort to codify it yet. As far as the repair, the code's largely sort of silent on that. The expectation is that the repair would be done reasonably quickly, but I don't have a certain section to point to that says you have 30 days or 60 days. Not like this in the 322 standard where you have construction work durations. You could probably use that if you wanted to, but to be honest, the condition's already been there for probably a year or 2 years or 3 years. So to say you've got 6 more months is not really the right application, but it's better than nothing. So, yes, sir.
Is there anything about 5G with the deployment of MIMO antennas that you see leading to increased number of modifications on towers? Do you see this changes having a whole, any?
Just because the antennas are getting bigger or heavier or things like that, you mean?
Yeah.
Potentially, sure. I mean, again, I'm gonna speak from the perspective of a tower owner, but the more antennas you get on your structure, the better your business is. So you're inevitably using up the capacity of the structure.
Yeah, I've never seen a MIMO antenna, but the fact that they call it massive MIMO, I think of something really big.
Right. I've seen, Tom, anybody else I've seen some dimensions of them before, and they are large. It's fundamentally you'd expect it'll probably eat up a significant amount of what the tower has in reserve. However, it also functions if you take the copper down and put fiber up, you may get a lot of that back. So when it comes to putting up bigger antennas, a lot of times the lines that you run up to them are just about as significant as the size of the antennas you put up. But where you're probably going to see the difference, I would expect, and I'll defer to you guys what you think, is really you're going to see in your mount designs. You'll see it impact towers, but towers, on average, like, again, I'm going to guess to say on average you see about between 5 to 10% of a tower, like the towers in the field that get active applications and new equipment put on, probably don't meet structural standards. That's probably in the ballpark, at least, of what we see at American Tower. But you're going to see that with mount analysis, I'd expect to be significantly higher. And I'd expect for those antennas that it'll affect the towers, but probably not as much as you think, and certainly with the standpoint that Rev H, by and large, reduces loads on towers, you may actually sort of get some of it back.
Yeah, we've already seen quite a bit of evolution on the loading for a lot of towers where just the advent of radios up on elevation have significantly increased the demand on your average level, and that potentially can increase with additional need for data driving through a single RAD center. So certainly hasn't been any real conversion to wanting to put less equipment up there to date.
I think we'll ever see that.
And maintenance of structures has been an issue. you know, certainly not with the larger tower owners, but, you know, when you get into owners that may own just a handful of towers or maybe even just a single tower, there's not really, there's very little incentive to maintain that structure. This, by introducing this, annex here, we're introducing an incentive to develop and maintain an approach of maintaining the structure. We're going to be able to increase the capacity of the structure. So as someone who is frequently on towers myself where maintenance is an issue, I'm anxious to see how, you know, smaller tower owners look at this and see an incentive to keep their structures maintained. I think there's a question over here.
How's the maintenance monitored? So if they want to fall into this program, do they have to submit, documentation of their maintenance of their towers, or they'll just assume they're doing it?
The only requirement is that you essentially state that you are using this annex. So within whatever analysis you are doing, it's clear that you are stating you qualify for the use of this annex. But beyond that, there's not a policing force out there reviewing these maintenance inspections. A jurisdiction may require submittal of inspection records. We have not seen that today.
I was gonna say, from the same standpoint, as an owner, the jurisdiction may require it. Probably what would inevitably happen if there was ever some type of damage to the structure where there's an insurance claim or, God forbid, something worse happens, this may be a place where you have to be able to provide documentation that you've done this. It's somewhat on the honor code, but generally these things have a way of working themselves out if you're not demonstrating the proper discipline.
If you're a third-party engineer or an owner, you'd be essentially reluctant to using this unless you establish that they have a good maintenance program in place prior.
That would seem to make sense.
This would be a part of your conversation with the owner as whether they want to take advantage of this and are they prepared to basically effectively invest in their structure by that capacity.
And ultimately, it's up to the engineer of record to decide whether or not this factor would be applicable based on the program that they have and the documentation that you have in place.
I'd be reluctant unless they have a good program.
Sure.
But again, there's an incentive now, right?
Yeah.
Perfect, thank you for that. Basically, it's the tower's way of saying thank you for inspecting it. That's what we boil it down to. Let's move on to mount analysis. It's been a trend in the industry for years, but recently it's been codified. Mike, can you walk us through a lot of talk has happened of how to analyze mounts. Can you give us a breakdown of when to analyze a mount?
Yeah, sure. I'm going to take a step back and talk a little bit about Rev G and kind of how we arrived where we're at with mount analysis in Rev H, and I'll try to be brief. Excuse me. Rev G, the intent with Rev G was never to not have a mount analysis required, although the language is a bit vague. And so that was kind of the basis of the conversation surrounding, well, how do we want to codify mount analysis in Rev H? And that kind of got us to where we are now. Rev H does give guidance in terms of the loading that is prescribed for mount analysis. It goes as far, for example, as to even require a 500-pound man load, which is a significant deviation from Rev G, which was at 250 pounds. And the idea behind that is that, in reality, we see more than a single point load on a mount, and there was some discussion about how to accurately take that into account in a mount analysis, and ultimately we arrived at a single 500-pound point load. Additionally, there's some guidance for mount analysis as it relates to rigging plans. Anytime a contractor is going to be rigging directly to a mount, there needs to be, depending on the scope of the work, there needs to be a site-specific mount analysis for that particular scope. To get into how it's applied, there is provision in REV H for when you need a mount analysis. Ultimately, what we arrived at is that if there's less than a 5% change or a 5% increase from original design or from the last structural modification, you don't need to do a mount analysis. What that effectively means is that you're going to be doing a mount analysis quite often. There's very few instances where an equipment change is going to result in less than a 5% change to a mount. Mounts are much more sensitive to small loading deviations than a tower, for example, where changing an antenna on a tower, you may see a 1% change. For that local mount that's holding up that antenna, you may see as much as a 50% change in usage for that. So there may be small cases where you're swapping out a TMA or maybe a radio where you can look at it and maybe get more of a desktop review, and an engineer will say we don't need a full mount analysis. But in most cases, you're going to be doing a mount analysis, especially if you're changing an antenna or anything of that nature. What we ultimately wanted to strive for with including the mount analysis in REV H is we wanted to have safer structures. When 4G started rolling out, we started seeing some examples of actual mount failures and large mount displacements from the increased loading, whether it was weight of the radios or wind area of the antennas. And so, seeing those real-world examples drove us to wanting to have a more stringent and exhaustive process for evaluating mounts.
Thank you. With that, we have time for one more topic. So if anything jumps out to anyone, let us know right now. Otherwise, I'm going to pick it. All right, let's talk about rooftop converging wind, as it is impactful, and probably not in the good way, but it will affect some sites in the future. Mike, can you break us down to what the converging wind methodology is or why it's happening?
Yeah, sure. This is an example of REV H kind of catching up to other building codes. And essentially what it is a new factor introduced that takes into account wind speed up, much like we do for topography, but this would actually be used for buildings that are greater than 50 feet in height or greater than 50 feet from surrounding buildings. If you can see on the picture here, that would be an example of a need to apply this rooftop factor. The factor is applied directly in the calculations. It's going to be up to the engineer to list or I guess report the use of this factor. But in most cases, the results, or I guess the impact of the structure, are significant, but not they're really not too bad. In a lot of cases, we've seen, I guess, wind loads increasing 5–10%. Very, very rarely, actually, I can't think of any example where I've seen an increase of 30%. There are some out there, but it really hasn't been as widely applicable as one might think.
So, an example would be like this hotel technically wouldn't qualify, even though there's nothing necessarily right around it that would have a wind speed up. You're really dealing with things over 50 feet tall, and that it's significantly higher than other buildings that are around that are over 50 feet tall.
Excellent. Thank you, guys. With that being said, we're going to wrap up this panel. If anyone has any additional questions or would like a breakdown of the other slides, please do let us know. With that being said, please know that for those of you that are going bowling, it starts promptly at 1 p.m. today. And for those of you that are going downtown tonight, the shuttle service starts at 5:15 p.m. That's when the buses will start running. Last bus leaves at 1 a.m. Whoever does that, God bless you. Also, the panel tomorrow, breakfast starts at 8:30 a.m. with the first keynote starting at 9:30 a.m. for those. Okay. With that, I'd like to thank you to all the panelists and for today's production.
Thank you.